Hey guys, universe is filled with paradoxes. For example, picture this: the vast expanse of our universe filled with galaxies dancing through the space. But what if I told you that within this celestial ballet, a cosmic mystery is unfolding, a tension that challenges our understanding of the cosmos itself? Welcome to the enigma of Hubble tension. The story begins with Edwin Hubble, who discovered that galaxies are moving away from each other. Now, this expansion is described by the Hubble constant, denoted as h0. It's a key parameter to understanding the cosmos. In fact, prior to Edwin Hubble discovering that the universe is expanding, it was an accepted theory that the universe was static. In fact, this theory was so strongly held onto, even the great scientist Einstein himself had to modify his equation so as to fit this static universe model. There are two methods of measuring this Hubble constant. One using local observation of nearby galaxies like Hubble Space Telescope, and the other one using cosmic microwave background or CMB. So what's the paradox? Well, the measurements don't agree. A local measurement gives higher expansion rate, while the measurement from CMB data gives a slower rate of expansion, and the difference between these two is as big as 10%. The Hubble tension with local observation comes to around 74.3 kilometers per second per megaparsec. However, the same Hubble tension with CMB comes to around 67.3 kilometers per second per megaparsec. Other way to put this is my height from head to toe is 5 feet 8 inches. However, from toe to head, it's 6 feet. It's like trying to measure the speed of the car with two different methods and getting conflicting result. The Hubble tension challenges our understanding of the fundamental properties of the universe. So there are two ways to measure the Hubble tension. One is the local measurement. It is aided by the Hubble telescope. In fact, the name given to Hubble telescope was not to tribute Edwin Hubble, but really to get to a conclusion about this Hubble constant. So how does it really get measured? Assume that you have got a light bulb like some 10 feet away. Now you know the brightness of that light bulb. Now imagine a house somewhere in the dark. You don't know how far that house is, and that house has a light bulb. Now, just looking at the brightness of that light bulb, you can, to some degree of accuracy, you can say that how far that house is. Translate that into universe. So we have got this Cepheid variable stars. These stars are basically super bright, pulsating stars to which we know the distance, and then we find similar stars in distant galaxies, mostly type 1 supernova, and then put in some mathematics in the mix, and then come to a conclusion that that galaxy is that distance away. We keep measuring this, and then we get the rate of expansion, the Hubble constant. And the other way is CMB, which is cosmic microwave background. CMB is the afterglow of Big Bang, the oldest light in the universe. It provides a snapshot of the universe when it was just 380,000 years old. So CMB data is obtained by mapping the temperature fluctuation or anisotropies in the cosmic microwave background radiation. Now these tiny temperature fluctuation across the sky represents the density fluctuation in the early universe. Astronomers use their tool to find the cycle of densities and then find the redshift to figure out the rate of expansion. In other words, let me put it this way: you see a picture of baby, and then you try to assume what would be the age of that baby today. Both these methods and both these ways of measuring the Hubble tension has error less than 1%, and they have been verified multiple times. The stakes are high because resolving the tension could lead to groundbreaking insights into the nature of the universe itself. Let me put it another way, like all the physics that we know of, we have put everything into determining the Hubble constant. However, still we're not able to figure out why we get two different values. To get the rate of expansion, really you need to get this matter and energy at any part of the universe. So assume that you have got a cookie with some amount of resin in them, and then you expand that cookie. The distance between the resins in that cookie is going to increase. By measuring and using some mathematics, you can get to know the rate of expansion. So we have got neutrinos, we have got normal matter, we have got dark matter, we have got dark energy. We have put everything that we know of, but still there's a difference. So either we have got incorrect measurements, chances of happening that is quite slim. In fact, it is 1 in a million, or there's a new physics that we don't know of. Now today mostly it is agreed to take somewhere in between. So somewhere like 71 kilometers per second per megaparsec is the rate of expansion of the universe. Until we find new physics or someone proposes some new theory, this debate is less likely to die down. Alright guys, if you have made to this part of the video, then you are more likely to subscribe, comment and share this video. Please do that, and I'll see you next time around. Bye bye.